From the previous video, we saw that in the case of elastic collisions, when two objects bump into each other, they end up bouncing away after the collision happens. So now what happens in inelastic collisions? The colliding objects stick together. So what does this mean? Again, suppose we have object A that is heading towards an object B, and object B is also heading towards object A. This is the before image. What happens when they collide with each other? First, we will see that instead of bouncing off of each other, just like in the previous scenario here, where the balls simply end up moving in the opposite direction, in this situation, the balls end up sticking to one another, forming one bigger mass. Now, what does that bigger mass look like? I don't necessarily know. It can look like something like this, two balls that are stuck to each other, or it can look like a larger ball, supposing these two, for example, are, I don't know, made, like depending on the material they are made from, they form a bigger object. So it doesn't really matter what the object looks like. But what matters is that in the after image, you form a more massive object that has the mass of A and B together. And this object will move in the direction of the object that had more momentum. So suppose A had more momentum and B had less momentum. That means this larger object will move in the direction of object A. Not necessarily in the same speed, but at least we know the direction. Now consider what happens in another scenario where it's a simpler case here, because suppose we have object A heading towards object B, but this time object B is not moving. So it's a static object that has no intention of moving, and object A is heading towards it. And we know that this is an inelastic collision. So we know that in the after image, these two balls are going to end up forming a larger object. And this object will also have the same mass as we said earlier, that it's going to be the combination of A and B together. This object will move in the direction of A, because automatically A will be, or will have, the larger momentum, given that B is just static, so its momentum is automatically zero. So knowing this, object AB in the after image, it's going to move in that direction. And it's definitely going to be slower than object A. And that makes perfect sense, because when you increase the mass, if you remember from before, the velocity ends up dropping. Now, what does this look like mathematically? Right now, for this section, we're interested in this particular case over here. This is what we're going to be looking at mathematically. So what are the calculations that can go on in this particular scenario? So we're not going to be looking at calculating elastic collisions cases, at least not just yet. And we're not going to look at this particular case where object A and B are moving. So let's start with the simplest case, where object A is moving, B is not, and in the after image, the combination of them is going to be moving. So what does that look like mathematically? When we look at the formulas, we're going to see that, or we're going to track the momentum of all the objects before and the momentum of the objects after. So what is the momentum in this before image? Given that object A is the only thing moving, then the momentum is simply the mass of A multiplied by the velocity of A. Looking in the after image, the total momentum is the same thing, more or less. It's going to be the mass of A and B together. So we're going to represent that as a capital M. And we multiply that by a new velocity. We're going to represent that as capital V. So this new momentum, so we're going to call this momentum before and the momentum after. So the momentum before is going to be equal to the mass of the moving object A multiplied by the velocity of the moving object A. And the momentum after is going to be equal to the mass of the total sum of the mass of A and the mass of B multiplied by the velocity of this larger object. So how is this interesting? How does this help us? Well, if we think about it for a moment, we're going to realize that given that momentum in a closed system is conserved, then this means that the momentum before is equal to the momentum after. So we can expand this even more and realize that the mass before multiplied by the velocity before is going to be equal to the mass of the larger object over here, represented by capital M, is multiplied by capital V, which is the velocity over here of the larger object after the collision. So we have this really neat and very simple formula. mv equals mv. And for a moment there, this looks ridiculous, right? It looks like a tautology. It looks like, of course, mv equals mv. But we know that this m is different than this m, and this v is different than this v. This m, this lowercase m, is the mass of A before the collision, multiplied by the velocity of A before the collision. And this m is the mass of this larger object, AB, after they collide and combine, multiplied by the velocity of this new object after these two balls collide with each other. So this m is not the same as this m, and this v is not the same as this v. But the multiplication of this m and this v are going to be equal to the multiplication of this m and this v. So it's a very neat formula to use, and we're going to look at an example. So let's look at this example. A moving car crashes into a static 2,500 car in an inelastic collision. The mass of the moving car is 2,000 kilograms, moving with a speed of 5 meters per second. Calculate the velocity of the cars after the collision. So let's draw this. It's always nice to draw, given that this helps us see the scenario as it's going on. So we always need to draw the same diagram, really. No matter what the exercise is telling us, we're going to be drawing the same thing, especially given that we know that this is an inelastic collision. So, what do we need here? We know that the moving car has a mass of 2,000 kilograms. So, the mass of this, the mass of A, is going to be 2,000 kilograms. We know that its velocity is 5 meters per second. Excellent. Now, the static car has a mass of 2,000 kilograms, 2,500 kilograms, and it's written right up here. So we know that the mass of this car, MB, let's call it, and we're going to call that MA, mass of MB is 2,500. They want us to calculate the velocity of the cars after the collision. So they want this velocity down here. So what do? First, we put in the formula just as we remember it. So we know that mv equals mv. And we need to think, what do we want? We want the velocity of the cars after the collision. Excellent. So we want this. We want this v, because this v is the velocity after the collision. Remember that everything lowercase is before, everything uppercase is after. So we want the velocity after the collision. To do so, we want to get rid of this big M. And in order to do that, we divide both sides by it. So we basically take this M to the other side, and remember, given that this is a multiplication, you can take it to the other side as such. And we're going to have this wonderful formula that says that the velocity, that big V, is equal to mv over capital M. So now we can start plugging in the numbers. So capital V is equal to mv over big M. So what is small m? Small m, if we remember from before, so this is when it's very important to remember your definitions. Small m is the mass before the collision, the mass of the moving object before the collision. And in this situation, we know that it is ma as 2,000 kilograms. So we're going to plug that number in, 2,000, multiplied by small v. And remember, small v means the velocity before the collision. And this is exactly what we have here, 5 meters per second. So 2,000 times 5, all over big M. Now, big M, having a capital letter, means that we're looking at what happens after. So this is the mass after the collision. And the mass after the collision is A plus B. So we're going to do exactly that. We're going to say that big M on the side is equal to mass of A plus mass of B. We know that A is 2,000 kilograms. We know that B up here is 2,500 kilograms. So we're going to get 4,500 kilograms as big M. Okay? Now that we know what big M is, we can simply plug it over here, 4,500. So we put these numbers on the calculator, and we get 2.2. Now, given that we're calculating velocity, our unit is going to be meters per second. And that's it. This is how we solve these types of exercises. It is really as simple as that. The most important thing is to remember that this M is going to be the total mass after the collision. Okay? Remember that capital letters are what happens after. So that's why we know that after the collision, in an inelastic collision, the objects stick together, so their masses add up. And that's why we plugged in this larger value in place of big M. So that's it for this video.